Welcome everyone. So last class we have seen what tensors are and what their representation in indicial notation is, and we have seen some elementary basic operations which are similar to those used in vector calculus, right? And today we will continue in the same line. We will try to see what tensor functions are, what are the common properties of tensors, and some more advanced operators on tensors. Okay, and we will end with a familiar concept, which is eigenvalues and eigenvectors. So that is how we will conclude this lecture. All right, so let's begin. So this is how we have defined what a tensor is, that especially a second order tensor, that it maps from a Euclidean space to the same Euclidean space, and it is a linear function, and a linear function has this following properties, right? And then we did some operations, right? So this is all familiar stuff so far. So we will begin with functions of tensors. Before we formally begin, let us sort of brush up what we understand as a function. A function can be a scalar or a vector function or even a tensor function. Furthermore, the value of the function can be scalar, vector, or tensor. Okay, there's a difference. It could be a vector function, scalar function, or a tensor function, and its value can also be anything. Okay, for example, let us see what a scalar valued vector function is. Okay, the output of this function, the output of this function is a scalar. So it is scalar valued, it's a vector function. Okay. Likewise, a vector valued function is a function whose input, okay, this you may ignore this underline. There's a function whose input is vector, output is scalar. There's a function whose input is vector, output is vector. What that function is, something is not which is of importance at the minute. But there is a function which takes in a vector, it gives out a vector. So it's a vector valued vector function, right? And there's something called as invariant. Okay, we will combine all these things. What is invariant and how it is, how we can call it, how it is a kind of function. All right. So invariant is also a kind of scalar function. Its input is a tensor. Okay. We at the minute are working with second order tensors, and in that there is a kind of function. It is a scalar function, and whose input is a tensor, the output is a number. Okay, it's a scalar function. And invariants are such functions whose value does not change whether your tensor is in coordinate system 1 or 2 or 3. Of course, all these coordinate systems are various kinds of Cartesian reference frames. Okay. So regardless of what your coordinate system is, this particular function, when you feed in A or A prime, the output will be the same. That is why it is called as invariant. So what are these invariants? Okay, little more warm up. Now we have seen scalar with vectors. Now let us try to see little more in vectors so that we will extend the same line of thought to tensors. Vector is a function, vector function of position. So speed is a function of position. Okay, so it is a vector valued vector function. Okay, and you can, that function can be anything. You can have a scalar function or as such when you write. Okay, so it is a vector valued vector function. Okay, likewise you can have various other forms as well. In vectors, we are aware of this, gradients. We will prefer to write it this way rather than this way. We will go for this notation, grad V. Gradient of V is a tensor if V is a vector in Cartesian coordinate system. We have seen already that if you have two vectors in the last class, UV is basically representing a tensor. It is representing a tensor. Now grad, this operator, del operator, is nothing but a vector, dou by dou x, dou by dou y, dou by dou z transpose. So this is also a vector, a column vector, rather a column matrix. Okay, so this is a dyadic product between del vector and the vector V. So a gradient of a vector leads to a tensor. Okay. Gradient of a vector leads to a tensor. I have written it in initial form and also in matrix form. Where is this used? The most common thing which we bank on, which is strain. Okay, we will define more formally how this strain is, how this strain is. But this is what gradient is in various forms. We are all familiar with this. Once you know a vector, we can identify it using matrix style or in initial style. Okay, so there are about 1, 2, 3, 4, 5 forms of writing the same, all representing the gradient. Right. So now let us use the same and extend it towards tensors. So functions of tensors. So scalar valued tensor functions. Okay, the input is a tensor, second order tensor, and the output is a scalar, which is invariant, or which we will eventually touch towards the end of this course, is strain energy density. I can represent it as E, and I can write it as a function of strain. The amount of it is equivalent to you thinking this was the strain energy density for a one-dimensional problem, half Young's modulus times normal strain square. So this is the strain energy density. It's a function of epsilon. Here epsilon was a scalar because you're only dealing with one-dimensional problem. But in general, it's a tensor, which we will rediscover. Derivative. Derivative with respect to a tensor. One can never write 3 by vector v. This is not really valid. But unless you formally define such an operation, which has never been defined. However, for tensors, there is a derivative which has been defined, and this is how it is being evaluated. Okay, you have a function phi or phi, and its derivative with respect to a tensor is evaluated this way. This is the definition. All right. So in matrix form, if you know your function, it could be a function of anything. Okay. If at all it is dependent on a11, this is what it is. This then you will have a non-zero term. Likewise, you fill in the remaining 8 terms. So this is how a derivative with respect to a tensor, which is in the, and derivative with respect to a tensor is defined. Okay, so nothing to panic. It's not like you are dividing by 0 or dividing by a vector or anything, but this is how it is being defined. All right, so derivative of a scalar function with respect to a tensor leads to a tensor. You see, this is a tensor. All right. So this is a scalar valued tensor function. So a scalar function, we try to take the derivative with respect to a second order tensor, and the output is a tensor. Where is this used? Typically in nonlinear mechanics, where you first define the strain energy as a function of strains and strain rates, and from there you try to identify what the expression for stress is. So that is where this particular use, it's a particular use of this scalar value tensor functions comes in primarily. Okay. Tensor function of position vector. What does it mean? I have a tensor and it's a function of position vector. So divergence of a tensor is denoted by del dot t or div t. We will stick to this notation. Okay, just to avoid all confusion. My intention is to just so that you know, certain books use div t, which is sort of an old notation. It's nice to use this notation with the dot visible. And in initial form, this is what it is, dou tji by dou xj. Okay, in index form, of course, the comma denotes derivative with respect to the last variable, not just j, but xj. That is what the last, the comma is indicating. Comma is indicating that particular partial derivative with respect to the corresponding axis variable. All right. So divergence of a tensor is leading to a vector quantity, as can be seen in this initial notation. And in matrix form, this is what it is. Some books may write things like this. Okay, it is incorrect. Okay, then they do this, but when they write div t, they actually mean divergence of t transpose. Okay, when they, So for example, a standard law which we will see is this, which is the force balance equation. And you have already seen the component form of it. This is dou sigma xx by dou x plus dou sigma yx by dou y plus dou sigma zx by dou z plus dx is, let's say we are dealing with a static, we are not dealing with a wave mechanics problem. So let's set this to 0. Okay. When they write such equation, instead of writing div t, they will say div sigma transpose. Okay. Those books, those references which define divergence of a tensor as something of this style or Tij comma j, either way, they when they write this actual divergence, they will, this particular variable becomes sigma transpose or the tensor transpose. Okay, so you'll have to be careful if you are following any other book of that kind. Okay, in our lecture, all in our lectures or in all through this course, we will intend to say indicial form is this because it is in line with also your mechanics of solids when you have analyzed the individual element. All right. So this is the same in matrix form. And yeah, as I said, it comes in the force balance equation. All right. So those books which define it the other way, when they write this particular equation, they'll use this. They'll put a transpose so that things get adjusted. Sort of an old confusion. It's nice to avoid. Most modern books use this. So let us stick to this particular notation. Right. Divergence theorem, same thing which you have already seen in the engineering mathematics courses. If you have a closed volume which is bounded by a surface, and if n represents the normal as a function of the position, so this is my origin, okay, and this is the corresponding position vector r. N is a function of position, and this r on the surface. R is belongs to the surface and not the domain. And the divergence theorem is this. This, can it be proved? It can be easily proved. You may want to start with indicial notation and prove it. Okay. In fact, one particular problem in the homework does cover the proof of it. All right. Properties. And as we defined, as we saw earlier, invariant is a scalar valued tensor function. We are talking about properties of tensors, and so hence we are referring to the invariants of a tensor, and in particular the second order tensor. So invariant is a scalar function of a tensor. So that means invariant is a scalar. The input to an invariant function is a tensor. The output is a scalar because it is a scalar valued function. The first invariant is what you are all familiar with, which is trace. Okay, and typically the invariants are denoted by the Roman numerals. Either you can denote it by the corresponding I sigma or I epsilon, depending upon what your tensor is. In general, it is represented by the Roman numeral, Roman capital numeral, which is sort of read in English as I. So the trace, what is trace? It's trace of a second order matrix is sum of the diagonal terms. So it's AII or AJJ, or for that matter in any invariant, right? It does not change with coordinate system. Same tensor, when you change the coordinate system, trace is such an entity that it will not change, right? Which you can prove it in a couple of slides, which we will. And what exactly is this trace? Which is this A11 plus 223 plus 33. And likewise, for that matter, any other coordinate system, right? Where is this used? Typically volumetric strain, which will come up in the next series of lectures. So when you're dealing with volumetric strains, it is easier to write it in terms of or represent it in terms of volumetric strains. Second invariant, sorry, that's a typo. It's not a trace. Second invariant, there is no, but it is involving trace, but it is not called trace. It's a function of trace, you may want to say, right? So it is defined this way. How does this defined? When we solve the eigenvalue equations, we will see it. All these traces in rather invariants, invariant 1, 2, all of them we will actually extract it when we solve a third order polynomial. All right. Please try to write this in indicial notation, this particular expression for the second invariant. Where is this second invariant used, or where does it commonly appear? It appears when you are dealing with things on plasticity. Okay, fracture mechanics, plasticity are a little more advanced courses which will involve all these concepts. The third invariant is something which you are familiar with, which is the determinant. And you can, how does this come? We already have seen how the cross product is defined. Cross product of two vectors is defined. So you can follow this notation, which is used as a mnemonic EI, EJ, EK to write and A1, A2, A3, B1, B2, B3, right? So you can use this kind of a mnemonic for determinant as well. Effectively, that's what you're doing, and that's how this expression is arrived at. Okay, there are various expressions which you can manipulate because you have a Levi-Civita tensor due to its peculiar properties. You can write the determinant of a tensor in various formats. I'll show you two other formats. This is one more. Of course, this is just changing the coordinate plane, coordinate axis, and this is one more such plane. All right. So why is this an invariant? We will see. Any other invariant which you may claim for a particular tensor should be in a position to write it as a function of these three variants, and hence these three invariants are called as principal invariants. Think of it more like an basis for the invariants. So you claim anything as an invariant. So you want to define a surface which is not changing, on which particular energy function is not changing, then you are clear, or mathematics tells you that it is actually a function of these three invariants, which means it has the properties which these three invariants bring in. Last one commonly used is isotropic and deviatoric plots of a tensor. In the last lecture, we have seen how, last and the previous ones too, we have seen how a given a tensor, how do we split it into a sum of symmetric tensor and antisymmetric tensor. Likewise, given a tensor, one can decompose it into isotropic and deviatoric parts. Okay, what is A tilde? A tilde is nothing but take the tensor, identify its trace, multiplied by the identity matrix, and subtract it from the original matrix. So that is the deviatoric tensor. That's how it is calculated. Original tensor minus identity tensor into the trace, into the or you can as well write this as A is the first invariant times identity tensor divided by 3 plus the deviatoric tensor. Just to differentiate the original tensor from the deviatoric tensor, we are using a delta sign. Right? Few more properties which will be commonly used using. One is the inner product. So inner product is defined this way of two particular tensors. Any two tensors is trace of A into B transpose. You know how to multiply two tensors, and you multiply A and B transpose, which gives you one more tensor, and trace of that tensor is a scalar. Right? So inner product is leading to a scalar. And you can, once you switch to initial notation, which you will be doing, each thing will follow from the other. And one more property, positive definite, if the inner product is some books, as I should have written it, some books also define inner product this way. Define as in denote, sorry. Some books also denote it this way. So if the inner product is greater than 0, is greater than 0 if A is not equal to 0, and if it is equal to 0 if A equal to 0, such a tensor is called as a positive definite tensor. Same kind of definition which is used in the theory of matrices. And since a second order tensor can be written in the form of a 3x3 matrix, most things which are applicable for matrix theory do hold here. And certain books define it in terms of post multiplication as well. Orthogonal tensor. If the inner product is 0, which means they are orthogonal. Norm. Basically, sum of its square root of some of its individual elements. Inverse tensor, as you can guess, it is A into A inverse should be equal to the identity tensor. Again, depending on the book, you may see it this way or this type. Okay. We are writing vector this way and tensor this way with one underline or single underline. A particular textbook may represent all vectors with lowercase and all tensors with uppercase. So you will have to pay attention to what is what. Yeah, otherwise they may simply write this. So it's not really clear unless you understand how he has defined a vector or a tensor. Okay, they may put both of them in bold, but vectors all through the book may be defined by lowercase letters only. Okay, so please be careful depending upon which book you refer to. It is important to understand the notations before the rest of the chapters are read. Cofactor again comes when is important when you take determinants. It is defined in either in terms of the inverse, or one can calculate the inverse from the cofactor matrix. Again, I made a notation or a theory borrowed from matrices. Orthogonal tensor is this. This orthogonal tensor is different from here I'm referring to two tensors being orthogonal to each other, and an standalone tensor being orthogonal. Okay, there it is, orthogonal tensors. The two tensors are mutually orthogonal when the inner product is 0. Here a tensor is orthogonal so long as product of it with its transpose is the identity tensor. Isotropic tensor. Isotropic, as it the name itself says, the tensor will not change even when you rotate your coordinate system, and there is a special form for it. So please stick to initial notation and try to identify the form of this tensor. What is the form of an isotropic tensor? When what is the form of an isotropic tensor? Basically, its components do not change even when you rotate the coordinate system. So what is that form of isotropic tensor? Please find out. Something you have seen, right? This part, geometrical meaning of a tensor, that it acts on a vector and gives rise to one more vector. So we can think of it more like an affine transformation where it has been stretched, scaled, and rotated. Likewise with additions, right? Now, there's one more property associated to a tensor. So a tensor has a basis, and all through we said we will try to stick to Cartesian. So with respect to Cartesian coordinate system, you can represent a vector in 3D space. You can physically draw it. Whereas tensor, you cannot represent it. You can represent it on an element, which we will do in about a few sessions, right? So given a vector, given a coordinate system, you can represent vectors, and the vectors have their basis vectors. However, you can also represent tensor on a particular element, not at a point or between 2 points. So once you have a Cartesian reference frame, which means you also have a set of tensors which are possible, and those tensors can act on vectors, and geometrically they do change the vectors in the forms as shown. Now, so every such tensor, any tensor belonging to a Cartesian coordinate reference frame, it is possible that sometimes when you act the tensor on the particular vector, it is as if that vector is only scaled. Its direction is not changed. Okay, you have a Cartesian coordinate system, which means you can, using the basis E1, E2, E3, right? E1, E2. So this is how we have defined, right? These are the 9 diodes. E1, 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 E2, E1, E3, E2, E1. So on like that, you had those 9 diodes. So once you have the 9 diodes, you can attach scalars and you can construct your tensor space. For any tensor given the Cartesian reference frame or given the coordinate system, it will have its corresponding eigenvector. What is that eigenvector? That eigenvector is such a vector if when you act the tensor on the particular eigenvector, It is as if you are simply scaling it. So this vector is as if I am multiplying the original vector with a particular scalar. Such vectors are called as eigenvectors. So given a Cartesian reference frame, you will have a tensor, and for every you will have a set of tensors which are infinite. For every tensor will have its corresponding eigenvector. What is that corresponding eigenvector? How do we find that out? It is such a vector which, upon acted upon by the tensor, is only scaled. Is it upscaled or downscaled? It's a different, that is not of concern. It is scaled. It is not being rotated. So the directions remain the same. Such a vector is called as an eigenvector. And the corresponding scaled value is called as the eigenvalue. So this is the geometric meaning of what are called as eigenvectors and eigenvalues. Okay. So every tensor of a coordinate system will have its eigenvalue and corresponding eigenvectors. Okay. So that is how I thought I'll lead you into this topic. Because normally this concept of eigenvalues and eigenvectors is done purely in a mechanical way. But now you know what it means in the physical space. So this is what we are claiming. We are saying if V was an eigenvector and if a tensor was acting on it, it is as if I have only scaled the original vector, where lambda is the eigenvalue, which is a scalar, and it is also called as the principal value. And the corresponding vectors are called as the eigenvector, and they represent the principal direction corresponding to the particular tensor. Okay, that principal direction is associated with that tensor. You change the tensor in the same coordinate reference frame, then it will have its corresponding eigenvalue and corresponding eigenvector. Right, so how do we solve it? So for us to solve it, you can do it in various ways. You can go the determinant way, or you can even try to do the initial way. So I've just written the vector as I've tried to take the post multiplication form on either side. So that's how I introduce the identity tensor. And for us to have a non-trivial solution, this is a system of homogeneous equations. For us to have a non-zero solution, the corresponding determinant of the coefficients must be 0, and hence we set the determinant to be 0. So as I said, for non-trivial solution, what is trivial solution? Trivial solution is where everything is 0. So apart from that, if you want a solution, then the determinant has to be 0. It's a second order tensor and the corresponding second order identity tensor. So we are essentially looking at 3 by 3 matrices, determinant of a 3 by 3 sized matrix. And if you solve it, since it is a 3 by 3 matrix, you get a third order polynomial. And while you do it, if you are encouraged to do the derivation, while you do it, because it's a standard mathematics, I've left this as an exercise for you guys to prove it. Simply take A, you know what is A11, A12, A13, so on until A33, right? Minus lambda times 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, then you identify the actual matrix, which becomes A11 minus lambda, A22 minus lambda, A33 minus lambda. Take its determinant and identify IA as first invariant, second invariant, and third invariant. And you know, given a third order polynomial, it is the sum of the roots, which is constant. Sum of products taken, two products taken at a time, is also fixed, which is the coefficient. So that's how these invariants have been defined. That is why given a tensor, these are its invariants, because these components do not change regardless of what is your coordinate system. Right, so third order polynomial will have 3 roots, lambda 1, lambda 2, lambda 3, and as I mentioned, the sum is equal to the first invariant, which is the trace. Second one is this. It can also be written as a function of traces. The third one is simply nothing but the determinant. Straightforward mathematics from here to here. Please do it. All right, so we identified, so we had a tensor, we solved the determinant, we got the characteristic equation, we identified the roots. Third order polynomial, so we got 3 roots. Those 3 roots could be unique or non-unique, or they could be all real or complex, right? All right. So how do we got the eigenvalues so far. Now let us see how does one identify the eigenvectors. So in order to identify the corresponding eigenvector, let us identify, let us take one particular eigenvalue. So let's say I'll pick lambda as lambda 1. Then I'll solve this expression and I need to identify an alpha and beta and gamma. So you'll solve three for, you take the first value of eigenvalue, which is lambda 1 here. Three equations, three unknowns. So you identify the unknowns. And hence you get the corresponding eigenvector corresponding to the first eigenvalue. Likewise, repeat the exercise to get further remaining two eigenvalues as well. All right. So that's how one calculates the eigenvalues and then the eigenvectors. Depending upon if you have three roots, right? If all of them, all the three roots are real and distinct, then the corresponding eigenvectors will be three mutually orthogonal to each other. If two of them are equal, then the mathematics will tell you the following. Okay, you pick the non-repeating eigenvalue. Say lambda 1 is non-repeating one. You take lambda 1, correspondingly you identify the corresponding eigenvector, which is E1. Okay, so until here you are fine. You are going to stick to the procedure which we just discussed. Pick the non-repeating value, identify its corresponding eigenvector, and then you identify the plane which is perpendicular to the vector and choose any two particular vectors in that plane which are perpendicular to each other. Then the corresponding vectors can be treated as eigenvectors. Choose any two vectors which are preferably perpendicular to each other. All right. Sometimes all the, if you get a perfect cube, then all three roots will be equal, and then which means every vector is an eigenvalue. So then choose any two orthogonal vectors, and that would lead your, that will essentially become your eigenvector. Right. So this is with respect to eigenvalues and eigenvectors. Most of you did solve eigenvectors and eigenvalue problems at some point of time, but this is more of a revision. But right now you would also know the physical interpretation of what an eigenvalue and eigenvector, what it does. All right. So this is perhaps this will be the last introductory lecture on tensors. From the next lecture onwards, we will define what a strain is, how a material is deformed, and from there on we will define strain, which is the infinitesimal strain, and based on that one can define other kinds of strains using these concepts on stresses, on traces and invariants. All right. So I will meet you all in the next lecture when we start with the applications of these tensors. All right. Until then,